Okay, welcome to the seminar. I'm very happy to introduce Shiva, who is graduating very soon and going out into the cruel world. Shiva will tell us about linear data structures and rigidity.
Thank you. So I'll talk about linear data structures and rigidity, and this is based on two works, one with Cyrus Rashtchian and the other with Anup. And so like it should be a slow and a simple talk. Please stop me with questions if some notions are not clear and so on. So yeah, okay. So let me right away start with the definition of like linear data structures. So these are motivated by trying to design algorithms for computing the inner products of vectors. So here we are given a query set Q that's a subset of f2 to the n. So I'm going to be throughout working with f2 to the n, where like it's vector space over like the finite field is f2. Good. And then also the goal is to be able to store. You want to store an vector x in f2 to the n, and be able to compute inner products of the form qx, which is nothing but sum of overall I of q of I times x of I. I'm going to use this notation for the ith coordinate of q and x, and mod 2, where q is from the set capital Q. Okay, so you know x ahead of time, and also you know this capital set Q. You're allowed, or you can pre-process x as using how much of a time you want and resources you want, and the query algorithm is going to get one q as input, and it should be able to output this inner product. Okay, and I haven't told you yet as to how or what the data structure is going to store. So what is stored is the data structure stores s bits are stored, where each of these bits are linear functions of x. So you're essentially going to store inner product of v1 with x, inner product of v2 with x, and so on, inner product of vs with x. So this is all access, or like this is all the information that you have about x, and the query algorithm on Q will access a subset of these stored bits to output qx. Okay, and what we want to minimize here is like, or the other parameter of interest is the query time, which is the maximum number of accesses, and I'll refer to the query time as t. Okay, so is the problem clear?
So you can always do with n queries by just using the like e1 to a.
Yeah, exactly. Yeah. So I'm going to say that next, but yeah, Thomas is right that like you can store, you can take s to be equal to n, and store the inner product with any basis or even the standard basis, and you'll take at most n time to be able to compute the inner product. Okay, and
are you assuming that the only way that you can pre-process and store something is by computing these inner products?
Yes. You're only allowed to take inner products, and that's all you can store. And yeah. So like this has also been studied in like a more general model where you can store arbitrary functions. Like each bit is an arbitrary function and not just being linear. But like for this talk, I'm just going to like think about linear. Okay. So the problem's clear. Yeah, and we want to understand the trade-off between s and t. Okay. Good. So now let's discuss some simple upper bounds for this. As Thomas said, one option is to store like x as e1 x all the way through en x. Here the space is n, and the time is like the maximum over q of the Hamming weight of q. Q in capital Q. Okay. Good. Another option to do is actually store q1x, q2x all the way through q size of qx essentially all possible inner products that the query algorithm wants to compute. And yeah, so here the space is size of q, and the time is 1 because you just have to do one lookup. So these are two, extremes that are there. Okay. So now, so now let me tell you what do we know from the load balance side. So the first claim is that the query time t, like any such data structure with space S, must have query time t at least log size of q divided by log S, and omega of this. Okay. Does someone see why this should be true?
Count the number of different options you can see by picking t values.
Exactly. Yeah. So the way to do it is like you are storing S bits, and the number of possible linear combinations with at most t vectors. This is at most S choose t times 2 to the t. And then, since the data structure is able to answer all possible queries from q in size of q, q in capital Q, this must be at least size of q. So this term is roughly S to the t, and this should say that t has to be at least log q or S. Okay. And so yeah, so maybe okay, I should say now that this is the best that we know for any explicit set q in terms of lower bounds. Okay. So I'll get back to it, but the second point is again for lower bounds, what if q was chosen to be at random? So if q is random, and size of q is say you pick it to be n squared, then we know that the query time must be at least n over log n with very high probability. Okay. And this is just the standard counting argument that I'm not going to show, but yeah.
This is for what S?
Yeah, good. Sorry, my bad. I should have said that. Yeah, if and S is say order n for now. Yeah. You store order n bits, and in this case, you get n over log n load bound with high probability. Okay. And the third point here is for explicit q.
So the first one will give just log n lower bound. Or no, it will give a constant lower bound.
Yeah, in this case, it will give a constant lower bound, yes.
But a random.
Yeah. But the random tells you that it should be as big as n, or n over log n. Okay. For explicit sets,
Gives you log n.
log n over log s. S is like n again, so.
Q is n squared, so you get 2 log n minus log n.
2 log n over log n. Sorry, this is like.
Oh,
Yeah.
I see.
Oh, yeah. Okay, so for explicit sets, what we know is if S is order n, then we know load bound of log size of q. Okay, so it's a bit of improvement over the log n factor, but yeah.
These are for certain explicit sets.
Yeah, so yeah, there exist explicit sets for which, yeah. So by explicit, I mean every point in the set can be computed by an algorithm whose runtime is it's polynomial in n. Okay, so that's what I mean by explicit. For instance, if you pick sets at random, these are not explicit sets because you'll need exponential time to actually be able to describe the set. Okay, so this is the state of affairs, and yeah, essentially all we know to do is this basic counting, and in the sense that it's an amazing open problem to actually beat the counting. Also, I should say that there are sets for which this is tight, so you cannot hope to improve this for all sets, but yeah. Okay, so far so good. Questions for the model? What's known? Okay, so now let me yeah.
One doesn't quite seem like an extreme case. Like for some sets Q, you could hope to get something smaller than N, right? Should we care about that case at all?
Sorry, which one?
For
this one?
Yeah. Like for maybe if like Q is really low dimensional, you could
Right,
do
yeah.
better. Do you care about that for the purposes of this?
No, maybe not. I'm going to assume mostly that like Q is full dimensional, but like yeah. Okay. So far, yeah. Okay. Good. Okay. Good. So far I only talked about like Q being like an arbitrary subset. So let me now give you examples for Q for which this actually is. Where there are like interesting algorithmic questions that are captured here. Okay, so some examples. So the first one is Q is nothing but the whole of f2 to the n. So in this case, like the query will get any point from f2 to the n, and you would want to compute the inner product. So in this case, what do we know? This is also sometimes referred to as the vector-vector problem. So here we know that like from the upper bound side, actually, yeah. So in fact, we know from both upper bounds and lower bounds that like if S is order n, then T must be theta n. So the best probably that you can do is just read all the bits off. So maybe you can only save on constant factors. And yeah, even if you want to go S to be poly n, then again we know that T is theta of n over log n. So there are upper bounds where like you can save a log n factor by like storing n cube bits, and we also know lower bound matching that as well. Okay. So the second problem that I'm going to talk about is the vector matrix vector problem. Yeah.
Third lower bound said Q was polynomial size? These explicit sets?
Okay, so like there's actually a spectrum. You can also have this. So we know of sets that are polynomial.
Example, Q is, yeah.
Yeah, so there are examples where these sets are polynomial in size. And this example is like 2 to the n. I'm going to show you an example where it's 2 to the square root n. So I think across like
so the overall problem is basically if you can get for polynomial size, let's say, better than log Q.
Right, yeah. Not even that, like anything where like it's little less than 2 to the n, like and you want to, it's like it's 2 to the little of n size sets, and you want to beat the log Q bound. That's because the example that I'm going to give you for the vector matrix vector problem is 2 to the square root n size sets. Okay. So here.
So the first example does not beat log Q. Because Q is 2 to the n, and you're getting only n. So the hard thing is to beat log Q.
Yeah.
I see.
And also also we don't, like for all of these problems, we also don't know any non-trivial upper bounds where like you.
And these are also deterministic algorithms, right?
Yeah, all these are deterministic algorithms. And, yeah. Good. So where was I? Okay. So I'll describe what the vector matrix vector problem is. So here you store a matrix M in F2 to the square root n by square root n, essentially a square root n by square root n matrix. And your queries are given by the pair UV in which are like 2 square root n length vectors, and you want to compute U transpose MV. Okay, so is the question clear? So just to make sure that we are like that this can be like thought of as the inner product problem is this because this is nothing but the trace of UV transpose with M, and this is nothing but inner product of 2 vectors that you get by just unrolling the matrix. So you just unroll UV transpose and then unroll transpose like the M transpose, and then you get 2. So this whole problem can be like So this also fits into this where Q or the query set corresponds to all vectors that come from rank 1 matrices, and you want to compute inner products here. Okay, good. So what is known here from the upper bound side? If S is, I think, order n, we know that is order n. If S is poly n, n over log n, and if S is, so from lower bounds we know that if S is order n, T is omega square root n. Okay, so there's a square root n gap, and then this square root n is exactly equal to size of Q. Sorry, log of size of Q, because here, so here size of Q is nothing but 2 to the 2 square root n, because it's all possible pairs of square root n length vectors. Okay, and like yeah. So essentially, like even for polynomial space, we don't know any upper bound that's better than n over log n. Actually, maybe this log square. I forget, but there's like a poly log n factor improvement that you get, but nothing beyond that. Okay, and again, yeah, here we're again stuck at log q, even though like yeah, you are the query set is like super large, and we don't know anything better than log q to prove. Okay. Good. Any questions at this point about the model, some examples that we saw, the bounds that I showed? No? Okay, good. So now since, okay, so we don't know how to improve this bound, or like, so maybe it's worth looking at maybe a slightly different or a simpler model than this model. So now I'm going to describe another model that's been studied called the systematic linear data structure model, and then discuss the same problem in that model, and then see some connections, okay, as to why proving these lower bounds might be hard, or like things like that. Okay. Good. So I have to now define the systematic linear data structures. So as before, again, you're given a vector x that you have to store, and a query set Q that's a subset of F2 to the n. But now the way you're going to store things, it's going to be restricted now. So you're going to store n plus r bits, where r is usually referred to as a redundancy. So what you do is you store inner products of x with r arbitrary vectors, and in addition you store just x as's. Okay, this is what is stored. So yeah, you store r plus n bits, and the query algorithm again will access a subset of these bits, but it's like accesses to the first r bits is free. Okay. You can also study the same problem where like you also charge accesses to the first r bits, but yeah, this is a different model where like you are actually given accesses to the first r bits is for free, but then every time you access like the individual coordinates, you get charged. So again, here we want to understand the trade-off between query time and r, no, which corresponds to the space previously. So is the model clear? Good. Okay. So let me tell you like a generic upper bound for this problem. Okay. Say your set Q is close to a subspace. Okay, so now I have to define what I mean by close. So say that there exists a subspace U, there exists say an r-dimensional subspace U such that for every q in Q, the distance, the Hamming distance of Q from the subspace U is at most T. Okay, so you have a set of points in like, you have a set of points in f2 to the n, and then you find a subspace so that all your points are like not too far away from the subspace. Okay, so does someone see if this holds? You get a nice upper bound for this problem. Yeah, and right. So essentially, these v1 through vr that you're going to choose are going to be the basis vectors for u. So you're going to store b1 with x all the way through br with x, where b1 through br form a basis for u, and then you store the usual inner products e1x all the way through enx. So anytime you want to compute the inner product q with x, this is nothing but u with x plus q minus u with x, where u is in u and the Hamming weight of q minus u is like at most t. Okay, so essentially like the inner product with the point that you want to compute. So this is q, this is u, from just reading these for free, and there's only you only need to make t hops to go from u to q, and then those inner products are can be obtained by just reading t coordinates, or making t accesses to the second set of bits that you have stored. Okay. Sorry. You know u, so you know q minus u, right?
I see.
So yeah, we're not charging, or we're not counting the time that it takes to find u and these vectors, but yeah, all you need to know is they exist, and you're done. So far this is good. Okay, so this really corresponds, this notion of being close to a subspace really corresponds to this notion of rigidity that was defined by Alan, Panigrahi and Yakhanen, and then we'll now show that actually the systematic linear data structure model is actually equivalent to this notion of rigidity that was defined by them. Okay, so now let me define rigidity, and then yeah, once I write it down, it will be clear why they are the same. Okay, so okay. Yeah.
For this vector matrix thing,
Uh-huh.
do you expect the right answer to be root 10 or 10?
I probably would believe it's close to n, and not square root n, but yeah. Yeah, towards the end I'll also outline an approach as to maybe how, or which can be used to get better lower bounds. Okay, so great. So let me define rigidity now. So rigid sets, and this notion is due to Alan, Panigrahi and Yakhanen from 09. So good. So yes, so a set Q, that subset of f2 to the n, is defined to be RT rigid if for every r dimensional subspace U, there is a Q in Q such that the distance of this vector q from the subspace U is at least T. So you take any subspace that's R dimensional, then you'll be able to find a point Q that's like far away from the subspace. And the distance parameter is T. Okay, so this is the definition of rigid sets due to them, and like for people wondering as to like what this has to do with the definition of rigidity due to Valiant. So in Valiant's notion, I forgot the year, maybe 77, I'm not sure. What you have is size of Q is exactly n, and instead of worst case distance, you have average distance. So expected distance must be T. Okay, so that's the difference. So here you work with worst case, and then you allow the sets to be larger than size n. Okay, and this actually is a very important definition, especially because if you produce like explicit rigid sets with good parameters, then it will imply circular bonds, especially for computing matrix transformations, like multiplying a matrix with a vector. So for that problem, good. So so now do you all see why these two models should be equivalent? Now that I've like told you like one part of the proof at least. Yeah. If it's not rigid, then you get an efficient data structure, and you can also go back the other way. Okay, so I'm not going to show the proof, but maybe I'll just write down the theorem that like and this is with Cyrus, and what we showed is that like let Q subset of f2 to the n be the query set, then Q is RT rigid if and only if any data structure with redundancy R must have query time at least T. Okay. So one way is what I showed is like if it is not RT rigid, then you get efficient data structures, but you can also go the other way. Okay, and proof is not hard. It's like essentially like the same thing has been defined, with different words and like yeah. So okay, good. So now about half an hour left. Okay. So before so the next goal is actually now that we have this connection between rigidity and these data structures. The question is, can you actually take some query sets from the data structure world and then try to prove better rigidity bonds for them? Okay. So before I do that, let me just quickly summarize like also some related work with respect to showing connections between data structures and rigidity. So recently, Devere, Golovnov, and Weinstein in like 2018, they showed that for the linear data structure model, like with space being order n, like they showed that any query time lower bound of little omega of log size of q times log n will imply new semi-explicit rigid matrices. So by semi-explicit, I mean like the runtime is not polynomial, but like it's polynomial with an oracle access to NP. Okay, so that was what was shown, but yeah, this is through the linear data structure model and not the systematic linear data structures. And then here we show like a direct connection and.
Is it Valiant rigid?
No, this is again APY rigid. Yeah. Because like if Q is n, then like you have a trivial data structure for these problems.
Rigid matrix, you mean rows of the matrix will be
okay. Sorry, my bad. Rigid sets. Yeah. But if you want to think of matrices, yeah, you just have the rows to be like points from the set. Okay, and for rigidity as well, like the best known rigidity bounds are like T must be at least n over r times log size of q. Okay, q over let me say n here. Okay, so again there is this log q bound sitting here, and we know of some results. One was actually given in APY, the other one by Alan and Cohen in 15, where they use epsilon bias sets and some expander constructions to get some bounds, but all of their results were like their sets were tight in the sense that the upper bound also holds. Okay, good. Okay, any questions at this point?
The ideal is to get what in this case?
Oh, the ideal is to get again T is n or n over log n. So like when r is like equal to constant times n, you get only a log q bound, but then random sets again give you n over log n style bounds.
For big R, you want to get log.
Yeah. Ideally for like r being constant times n, we want to find sets so that are far away with the distance of constant times n again.
How big are the q's in their constructions?
Actually, it's a parameter that can be varied. It can go from all the way from polynomial to depending on how you vary it with n. Yeah, it will also get to exponential, I think. Yes. Yeah, and one that's based on epsilon bias sets is like exactly what you have for epsilon bias sets. I think n over epsilon squared, and epsilon becomes a parameter, and you get roughly log 1 over epsilon as the lower bound. Okay, good. Okay, so I see. So actually, I'm going to push this here. Okay, so now I'm going to tell you how. Yeah.
Are there some candidates for these?
Yeah. So for this, I'll show you UMV is this vectors that you get from this query problem, or like the vector matrix vector problem is, I think, a good candidate. There are also candidates from codes that are there. Yeah. Good. Okay. Sorry, I'm like a little confused as to. Okay. So now, the next. Okay. So now that we have seen the equivalence, now I'm going to show you like that you can look at the set of vectors that you get from these rank 1 matrices, and actually prove a rigidity lower bound for them. Okay, so let me first start with the definition. So I'm going to define vector of a square root n by square root n matrix is nothing but it actually opens the matrix up into a vector 1, 2, 3, so on. And then like I'm also going to use MAT of the vector to be the matrix that you get. Okay. Good. So now let's write down what the set of vectors that we get from these queries. So define this set VMV to be nothing but all the vectors that you get by unrolling it of all like UV transpose for UV in F2 to the n, square root n. Okay, and what I'm going to show you is that the theorem, this also work with the Cyrus, is what we show is if R is at least square root n, then VMV is RT rigid with T at least n over R times log Q, which is n to the 3/2 over R. And I'm ignoring some constants here. Okay. For example, if you set r to be constant times n, you get that like it's the distance parameter for rigidity is square root n. Okay, but if you set it to be very small, like close to square root n, then you get like omega n as the distance. Okay.
So this just matches the old.
Yeah, it exactly matches the old bond. Yeah.
The APY stuff.
Yeah. And yeah, it's like it's not clear if like we don't know of any upper bounds like getting anywhere near here, and we don't know what's the right answer. But yeah, it's a nice open problem to like actually improve this bond. Okay, so is the statement clear? Okay, so let me prove this. So it's not too hard. Okay, I'm going to use the other side. Good. So great. So let U be a r-dimensional subspace. So we want to show that there exists a like UV such that vector of UV transpose is at a distance of at least n to the 3/2 over r. Okay, this is what we want to show. So like let me write down a key claim, and then which will actually imply this bound, and then I'll go ahead to prove that claim. Okay, so the claim is that there exists a vector like y in f2 to the n such that the distance of y from the vector space U is at least constant times n, and the rank of if you look at the matrix that you get from y by blocking it or like cutting it into square root n pieces and then making a matrix out of it, this is at least or at most 2r over square root n. So is the claim clear? You can find a vector that's far away from the subspace and also have just the property that like its corresponding matrix has low rank. Okay, so does someone see why this is sufficient? Okay, I'll write it down. So you can write matrix of y to be A1 B1 transpose all the way through A of 2r over square root n, B of 2r over square root n transpose. Right? This is just writing the matrix as sum of rank 1 matrices. Okay? So now we know that if you take if you look at the
So why do you know that
the rank is small.
why do you know that the rank of y is small?
Yeah, so I'll prove it to you as to how to find such a vector y with a small rank as well. If you just
He's using the claim to prove the main result. So the claim is
Oh, I see. You're assuming the claim.
yeah, I'm assuming the claim. I'm going to prove the main result, and then I'll come back and prove the claim.
Okay, but you've got the okay. No, that's right. Okay, fine. Yeah.
Okay.
So
Yeah.
you assumed you got a small rank matrix.
Yeah, and then you can write it as like this 2r over square root n sum of these many rank 1 matrices. So now we know that like y is nothing but a vector of each of them. Right? And we know that the distance of y from from u is large, is at least c times n. So this should imply that there is one vector in the sum that's also far away from the vector space. So that means that there exists, that means that for some I, distance of vector of AI bi transpose is at least the Cn divided by 2r divided by square root n, which is what we want. Sorry. Okay. So the key somehow seems to be finding this vector whose like corresponding matrix is also small rank. Once you do that, then you're done. Okay. Okay. Good. Okay. Can I? Okay. I will use that part of the board. So does someone see how to prove the claim? That's also basic counting and nothing fancy. There's one trick. Okay, so first, is everyone convinced that if you do not have condition 2, then we are in good shape? Because just by basic counting, if you look at all r dimensional subspaces, if r is like say less than n over 100, then there should always be like one vector that's like distance at least c times n from it. Okay, because subspace itself will not have large size. Okay, good. So now all we have to do now is like to make sure that we choose this y carefully to get to the second point. Okay, so this is where I'm going to use like a small amplification trick. What I'm going to do is I'm going to look at my coordinates 1, 2 all the way through n, and block them into like group them into like 2r size blocks, and call the first set to be S1, this to be S2, this to be S2, sorry, n over 2r. Okay. So now I'm going to consider subspaces Vs1 all the way through Vs n over 2r, which are just projections of u onto S1 through Sn over 2r. Okay. So each of these, so the dimension of Vsi is at most 2r. Sorry, is at most r, because each u was, so the u that you started off with was dimension r. Okay. So that means there exists a y prime in f2 to the 2r such that yeah.
S1, you pick the first 2r coordinates and you patch it with zeros.
Or
You
like,
want it as a subspace of R2.
yeah, you can. No, I'm looking at it as a subspace in like f2 to the 2r.
So how do you project u onto that?
So you just look at all possible values that you take in the first 2r coordinates, take the span. Okay.
So for the second one, you look at the first.
Yeah, the second 2r of them, and then take the span. You just keep doing it, and then it will also have dimension at most r, because if one of the projections had dimension more than r, then you would have dimension more than r. Okay. So this is, and then now the key claim is that like there's a y prime in f2 to 2r such that the Hamming distance of y prime from each of these is more than some constant times 2r for every I. The point is, the previous counting we know that like in 2r dimensions you want to find a point that's far away from an r dimensional subspace. That by standard counting, or like we know how to do it, but we don't have too many of these subspaces, so still the same counting argument works. So if it's not clear, like if the proof is not clear, it's okay. But all I'm claiming is, since there aren't too many of these subspaces, you still can find a vector that's far away from all the subspaces. Okay. So now let's look at this vector y that's defined to be as y prime concatenated with y prime concatenated with y prime. Okay, now by just this definition we know that the distance of y with u is at most c times 2r times n over 2r. because in each block the distance was at least c times 2r. There are n over 2r blocks, so the overall distance must be at least c times n. Okay, and the trick about the rank comes up now. If you want to actually write y as now a square root n by square root n matrix, you first write y prime. You break up y prime, or like break it into like 2r over square root n rows, and then you repeat it. This corresponds to y prime, this corresponds to y prime, right? And then the rank of this matrix can be at most 2r over square root n, because those many rows are unique, the rest of them are repeated. So this will give you that the rank is also small. Okay, it's a simple amplification trick in the sense that I just looked at, we know how to do things if R was n over 2. I just used that idea to break it up, the whole space, into those many.
But then the proof seems to do something stronger, right? Because now you actually don't need all rank 1 matrices in this argument. You just need your y that you chose can be expressed as a sum of a much smaller set of matrices, because it's actually repeating coordinates.
Right. Yeah. Yeah.
Like there's an even smaller space of matrices which is rigid.
Right. Yeah. Good. Yeah. Yeah. Only like the top some number of rows matter, and beyond that nothing else. Yeah. Good. I didn't observe that before. Yeah. Good. So is the proof clear?
Yes, so I just had a unrelated question. So you have this set, and the conjecture is that it has a better rigidity than what you proved.
Right.
And so my question is, so you can measure rigidity in infinite dimensions, like infinite fields, right?
Right. Yeah.
And would it be bigger or smaller or than the n over f2? So I'm just thinking, for example, have you studied the rigidity of this set over the infinite field?
So the thing is, I didn't, but all these arguments will just go through.
Yeah, I know these arguments would go through.
Right. I don't know if you get anything better if you work over reals or complex.
I mean, it may be easier to first study it over infinite field.
Right. I don't know an answer.
You use
Like reals.
what distance?
I don't know, L1 or L2.
If you use L2, it's kind of like about the singular values, right? We're talking about the distance from subspace. So
Yeah, I think L1 probably, but yeah.
I think L0 is what it corresponds to.
I mean, the reason I'm asking for infinite field is that I understand it's hard to argue such a thing, that there is no space, or yeah, so that for every subspace there is something which is hard. But if you're in the infinite field, maybe you can write some convex relaxations and study that. And I don't know if that would give something.
I don't know. Good. So I have like about 7 minutes. I'll end with an open problem that Anup at some point asked me, and then we thought about it for quite some time, and I'll tell you the problem. Where is? I'll write it here. So this is actually like the approach that I'm going to show is like is graph theoretic, and it holds both for like linear data structures, rigidity, and like all these related problems. So that I discussed here. So it's a question about Cayley graphs. So let me define the graph first that I have in mind, and then I will describe the question. Okay. So the Cayley graph on f2 to the n. So here the vertices correspond to vectors from f2 to the n, and you have an edge between. Okay, and then you have a set of generators S, which is a subset of f2 to the n, and think of size of S to be equal to order n. Okay. So now you have a edge between u and v, if there is a y in S such u plus y is v. Okay. Good. So is the graph clear? I'm picking some order n set of generators, and then I'm looking at the Cayley graph that you get, where like an edge exists if you can go from one vertex to another using some vector from the generator set. Yeah, exactly. Good. So now let me like tell you the question or the observation here. So if you start at the origin, like all zeros, and so you have all 2 to the n vertices. It's a bad drawing, but sorry, I won't try. But then just consider or look at the vectors that correspond to or come from your query set. This means that it okay. If you know that the distance in like from the origin to any q in capital Q is small, then we have an efficient data structure. In the linear case. Is that clear or no? All I'm saying is now,
I guess the part you left out is that S corresponds to the set of stored vectors.
right, yeah, sorry. So S is going to correspond to set of stored vectors. So what does every path in this Cayley graph correspond to from the origin to your point in the set is a linear, it actually corresponds to a linear combination of a subset of vectors from S, right? And if the path length exactly corresponds to number of vectors in the linear combination, and if that is small for all of them, then you can express your set Q as using just small number of linear combinations, which correspond to the query time T. Okay. So now, if you want to prove a lower bound on like linear data structures, all you have to now argue is that for any set of generators, the distance of your points that you care about in this graph is going to be far away. Okay, and we know that if you look at all 2 to the n such vertices, this distance corresponds to the diameter or the half the diameter, and that's going to be large. Because any Cayley graph with like order n generators, the diameter should be at least n over log n. But here we don't care about the whole graph, but we care about a subset of these vertices. And one potential subset here can be what you get from this UMV problem, or you can like try many other sets for which this distance could be large. Okay, and yeah, also it's nice because like we know a lot about the eigenvalues and the eigenspace and like what for Cayley graphs, and yeah. Maybe that will help. Okay. Yeah.
If the distance is large, you get that you can't get your answer by adding a few of these
words. Yeah.
But is it also true that you can't get it from any function on these queries? Like, I mean, you have some values. Maybe you have to interpret them in some other way than just adding them.
Like, what do you mean by values? I don't understand.
So you have these inner products of VI's and
right, yeah.
X. You're accessing like the length of paths.
Right, yeah.
Number of those things. And yeah, if you just get them and add them, then you get inner product of X and your
correct,
query.
Yeah.
But I'm saying, is it also true that you need to query all those things?
Okay. Yeah, I think it requires a little bit of proof, but without a lot of generality, you can assume that like the best the data structure can do is like be able to write it as a linear combination, because the data structure can only do linear stuff.
Yeah, if it's doing something else, you can reduce it to some other linear combination.
Yeah. it has to be consistent with what it does with the basis, and hence that will. Good. Any questions? If not, I'll I'm done. Thank you.